Thank you for making the time today. My name's James Harris and I'll be presenting the results of my dissertation, which is on simulations of radiation therapy. That is a gate Monte Carlo model of a flattening filter-free Varian 9 linear accelerator. And I'm very proud to have Dr. David Pfefferlé and Dr. Pejman, Rowshan, Farzad as my supervisors. So kicking off, we're just going to go through a bit of an overview of what we're going to be talking about today. And so we're going to provide a bit of a brief introduction into Monte Carlo modelling, what that is and how that works, the materials and methods which I've used as part of my...
When they haven't sorted out the result, I told them sort out the result, maybe we'll discuss it tomorrow if we have a chance. Yeah. One check there.
Sure thing. And so what we'll do is we'll then go through and discuss the materials and methods which I've used, have a bit of a results and the discussions which I've found, and then go through some of the challenges I've had and the potential future work that we can do. So kicking off, Monte Carlo modelling. What is that? So Monte Carlo is actually the art of using probability, statistics, and random number generation to mimic and imitate real-life phenomena. So there's many applications, and it's used in engineering, physical sciences, such as physics, biology, and chemistry, economics, and climate change models. So how does that work in our situation with physics? So what we say, we have an atom with the electron that comes through and it actually wants to, sorry, not this one. So we have electrons in itself there and we want to simulate electron interactions with an atom. So with that, we're aware that there's 4 different modes of different types of interactions that can occur, but each of those is dependent upon several different factors such as the electron's incident energy, the density of the material, the atomic number, and the electric and magnetic fields. And so each interaction of an electron is known as a history. With the photons, it's very similar. So we have a photon which is incident on an atom in itself. There's 5 different modes of interactions. Each of it all have a probability which is dependent upon all these different factors. So Monte Carlo modelling in itself puts all these different probabilities into a database that it then extracts, and we build an environment and we generate a beam of particles, be it electrons or be it photons. And then what we can do is then we can track and record how these particles interact, and we can simulate that using random number generations to simulate which events of these will occur based upon the probabilities and the properties of the environment that we create. So with that, it's very common for a lot of people to do this with a build Monte Carlo models of radiation therapy in itself. And so it's not an uncommon thing. It's actually been done quite extensively with a few different other people. Each of them, though, have used a different type of code. They've used different types of particles, different beams, and with that, they've discovered there's different beam energies. They've also used a different number of histories, and what they've done is they calibrated dose measurements made in a Monte Carlo simulation of a radiation therapy instrument to that of a commissioning data. And there's different modes of validation which they use. So as you can see, there's quite a few different types of codes such as GARN4 or GATE. There's some common ones, but there's also some other ones like MCMP, EGGS, NRC, and Topaz, and so on and so forth. So it is stuff that has been done beforehand, but the intent is for us to be able to use this in future work with other students as well. So we'd need to validate and calibrate that to our own data sets. And also with this, with our code that we do have, we're able to add in different features like MLCs and change the environment with it there. So moving forward into the materials and the methods with it. What we have to start off with first is we have to essentially go through, and there's a lot of different programming languages which are required to set one of these things up. So in our case, the Linux operating system is actually the best one to be used. But with that, to generate or to actually compile GATE in itself, there's several other dependencies, about 18 other program dependencies which need to be downloaded and installed. And with that, then you can start to see makes a requirement for us to actually install some of these components. And then there's the programming language of Gate, and that's where we're able to actually build the different environment, run these different simulations, gather our dose measurements, and then compare that to our own data. With that data analysis there, these are actually large files up to a 0.5 gigabyte in size that we're often analysing. So we need a software tool like Python to go through with that, and in some cases we need Root, which is a C++ based program built by the developers at CERN. So with that, how we apply the Monte Carlo modelling to radiation therapy, what we can do is we can get the schematic designs of a LINAC head. And then what we can do is we can simulate the initial electron beam and focus that on the target in itself, and then go through and build the weld environment so that we've got the collimators, the monitoring chambers, flattening filters if required, and different XY jaws, and then a water phantom at the very bottom. So on the left is the schematic diagram which was provided by Varian in itself, and so we're able to actually build that in the build that weld and build that environment in Gate, which is seen on the right to the exact specifications with the exact materials in itself there. From there, what we're able to do, what we're going to be doing is building build an electron beam that then goes through and hits that target, and then we're going to simulate all these different electron interactions and the creation of photons through Bremsstrahlung interactions, and then we're going to track those photons in itself as it continues to propagate further down. In order to save computational time, what we're going to develop is what's known as a phase space, and that can be seen by this grey disk, which is here. So this disk is about 20 centimeters wide and is about 1 nanometer thick. Now, the importance of this phase space is that whenever a particle crosses that phase space, its energy, its direction, and its properties are all recorded in there. Now, the benefit of this is if we're going to be going through multiple different simulations in itself there, we can actually use this as a bit of a checkpoint so that we don't have to continually re-simulate all those interactions which occur prior to that point. The benefit of doing this at this point in the XY, just before the XY jaws, is if we want to change the field size for the different dose measurements that we're going to do, rather than simulating from the electron beam hitting the target, we can just sample from this phase space, which will significantly decrease the computational time. So with the process of what we're going to go through, there's about 3 hyperparameters of that initial electron beam which we can fine-tune, and that is the mean beam energy. It is also the electron beam energy standard deviation, and then also the full width half maximum spot size of the electron beam hitting that target. From the literature reviews and different attempts at it, it's been determined that these 3 parameters are actually the most sensitive to changes in the dose deposited at the water box. So how we're going to go through and commission, well, not commission, in terms of validate how our model works and improve those hyperparameters, is we're going to go through and do some simulations, and then we're going to simulate a water box as well, which will be located at the exact specifications which are usually done with the commissioning data test as well. So what we've done what we do have the commissioning data for the Varian 9 linear accelerator, and all the different field levels going from 2 centimeters by 2 centimeters all the way up to 40 centimeters by 40 centimeters. Starting off with the 40 centimeter by 40 centimeter field, we're going to simulate that in this Gate simulation, and then we're going to simulate the dose which is deposited inside this water box as seen in this blue center here. Now, with this simulation, what we do have to do is we do have to define what the voxel size is that we're going to be recording the dose in. This can be a bit of a challenge because with the commissioning data, the resolution is down to 0.2 millimeters. And if we were to carve up that water box into 0.2 by 0.2 by 0.2 millimeter voxels, we will actually run out of memory on the computer. Doing a simulations, using voxel sizes of 1 millimeter cubed, that requires half a gigabyte in a memory in order to save that dose file. So that in essence, if we go, say, if 125 times the size of that, you can see how we'll run into challenges there. So with this simulation, what we started off with was just by 64 millimeter cubed voxels. So that was 4 mils by 4 mils by 4 mils. And then what we're going to do is we're going to compare these voxels, dose profiles, to that of the commissioning data in itself. And then doing a mean square error reduction, we would then go through and then find out which hyperparameters we're able to fine tune to get the minimal error. So with that, that goes through with what our aims were to actually go through and do dose measurements at all the different field sizes and compare that to the commissioning data with all the different field sizes. And ideally, our objective will be to get this within 3% uncertainty against the commissioning data. The reasoning for this is with the radiation therapy treatment in itself, the treatment plans are permitted to have a 5% total error between the treatment planning system and the measurements of the LINAC accelerators. And with the QA/QC testing, there's a 2% tolerance which is permissible under the current guidelines. So if we're able to get this within 3% error across the entire profile, then we'll be able to use this in the treatment planning systems. So that's the ideal goal of what we're trying to achieve. Going through to the results and discussion on how we've fared with this. So with this, we went through and we sampled all the different mean energy sizes. So we went from 5.5 MeV all the way up to 6.5 MeV at 0.1 energy increments. And so we created phase spaces at that predefined location. And what we did was we minimized the energy first, and then we went through, and once we found the minimum energy, we went through and did the same thing with a range of values for the standard deviation of the electron beam. And then finally, based upon the minimum energy, mean energy, and standard deviation, we went through and we spanned the full width, half maximum, different sizes. In total, there was 26 different phase spaces which we created, and this is an example of one that we have here. On the far left, this was for 5.9 MeV, and we utilized we got 2.5 times 10 to the 9 particles within this phase space in itself there, and it's got a very nice curve associated with that there. One key point to pick out is this little peak that is here, roughly around about 0.6 MeV. So that was associated due to the pair production. So we see a lot of a peak of that occurring with that there. So and then what we have is we have a very symmetric XY distribution of where this goes. And then similarly with the angular distribution, it is very nice and nice and close to just being straight on. What we have here now is just an example of the different dose profiles that we would have in the simulation and also the commissioning data. So on the left-hand side, what we have is the standardized commissioning data in itself there, which is all nice and smooth. And this was for a 40 by 40 centimeter field size that we used. And then on the right is what we have is with the simulated data. So it's looking quite nice. Again, this was for the 4 mil by 4 mil by 4 mil voxels. And the tricky parts are often on the penumbra side of things here with that alignment, because it's not the exact same size as the commissioning data, which has a 0.2 mil resolution. We did have to perform some volume averaging effects to try and align the commissioning data to the simulated data, which was quite tricky in itself there. This here is a bit of an example of what we're talking about. On the right, what we have is a bit of a misalignment where we were one voxel across. What that represented is a peak in the difference between the two on the right, and a negative peak, on a positive peak on the left and a negative peak on the right. Whereas what we would like is just some random noise all across the side there. Then moving through into the error calculation. So in this, on the graphs that we have on the right here is what the difference between the commissioning data and the simulated data is for both the X and the Y profiles. So the X profile is in blue and the Y profile is in orange. Now, with this, it was a bit tricky because the commissioning data was provided in a percentage depth or in a percentage dose, and the simulated data was in absolute dose. So what we had to do was we had to calibrate the commissioning data into a absolute dose so that we could do the comparison. The challenge that we had with that is that because there's so much random noise with the simulated So are you guys still there?
Yes, yeah.
Beautiful. So what we had to do was take an average of the dose at D max for the commissioning data and an average of the simulated dose at a depth of 15 millimeters. And then we were able to take the ratio of those to use that to calibrate it. It was worth noting that the actual error was very, very sensitive to this calibration in itself there. Initially, we were trying to pick a single point, but it fluctuated significantly due to the statistical error associated with Monte Carlo, hence the reason why we went with the averaging over a certain range. Another key point to note, it was the error in itself decreased with depth. This is not something which we initially intended, as it was as you would have predicted, there was more random error the further you go down. However, this made a bit of sense due to the statistical error going down with the depth. So because there was more interactions, the further down is less dependent upon the statistical error of Monte Carlo simulations, whereas further up, there's a higher dependence on that statistical error. So going through, as I mentioned beforehand, what we did do was we then took the mean sum of the error differences. So just quickly going back, we just took the square of all these different values and summed the square of all of those values. And so with that, we then did that for the mean energy, and we plotted the mean energy and then fitted a quadratic curve to that there, which provided we then found the minimum of that quadratic curve, which turned out to be about 5.88 MeV. And then we then went through and generated 6 different phase spaces for the standard deviation, performed the same error calculation across those profiles and the same curve fitting. And then we did the same thing with the full width half maximum size. With the final results, it ended up being about 5.88 MeV and plus or minus 0.2 MeV, with a full width half maximum of 1.39 millimeters. What we then did was we then ran the dose simulation for a formula by formula voxel again, and then these are the results. The 2 black lines represent plus or minus 3%, and so it gets quite close to within that value in itself. However, there was a couple of outliers with that there. This is due to the statistical error, and it can be rectified by running higher simulations, a higher number of simulations with this. So there we go. So there you go, 5.88 MeV and plus or minus 0.234. What we did manage to achieve, though, is at a depth of 15 millimeters, 92.4% of the voxels were within a 3% tolerance. and 97.6 were within a 5% tolerance in itself. So as I mentioned, it does get quite close. There were just a couple of outliers there, but running through with a higher number of primaries from that phase space in itself there, we should be able to get that error down. So just with some final thoughts on that, there was a lot of challenges associated with this project, namely the number of programming languages that you do have to try and learn to wrap your head around all of this. In addition, there's with the error troubleshooting, there's not much information available online. So you do have to start to become familiar with reading the error logs, which are outputted by the computer. Thirdly, it was the computational time which was required to perform this. Each of these dose profile calculations took approximately 24 hours to complete, and over 150 different dose profile calculations were run over the course of this in itself. And that should say, with the future work, what we do have is we could look at exploring whether there's a quartic or a quadratic relationship between some of those different variables. We just initially went with the quadratic approach. Additionally, we can investigate further. There was what the impact is on the full width half maximum on some dose profiles. We did get some peculiar results at the 3.5 millimeter profiles there. So further investigation could be done into exploring why that might be the case. And also there's different filtering techniques that we could use when calculating the dose measurements. Additionally, we could look at adding a multi-leaf culminator into this program and then using a GUI interface so that we could look at exploring the upload of patient CT data with that and using in treatment planning systems. Finally, there was in terms of some achievements as part of this project, I did manage to go across to the Moffat Centre and attend both the Moffat 10 and Moffat 11 integrated mathematical oncology workshops. And with that, I was successful in winning that integrated mathematical oncology workshop this year. And I also managed to complete the Geon4 advanced simulation course, where we've identified some additional features which we could add into this. So, and this is just a bit of a slide in terms of what we did at the IMO 11. Which was very, very happy to be a part of this year. So, and I think that's it. So I'll pause there for any questions.
Yeah, thanks, James. Any questions from James?
I have a question.
Yes.
James, it's wonderful work. Thank you very much for the nice presentation. Just one thing about where you were comparing the data, the depth of data, and one was absolute and one was relative.
Yes.
So you converted the relative to absolute. Wouldn't it be easier if you converted your absolute ones to relative and then compared the PDDs?
Yeah, so the initial thought was that was an initial thought to do that. However, we did want to provide an absolute error which was associated with that as well. So that was the thought behind converting a percentage dose into absolute dose so that we could continue with the propagation of error.
I see. Thank you.
Thank you, Martin.
Thanks, James. Terrific. Do you know how the parameters you end up with compare with other published models?
Yeah, so the parameters were quite similar. So let me just, if we go back up, so with just here, so you can see I got 5.88 with plus or minus 0.243, and with roughly 1.4 mil with the beam size there. So going up to these ones here, you can see it's kind of within that ballpark. With Texera had 5.8 with plus or minus 0.17. And then he had a full width half maximum beam. He didn't calibrate the full width half maximum beam. He actually just went with a specified 2 millimeter one with it there. Yeah. And then I think there was, a few with a Grevelo over here too. he had a 5.8 MeV, but he had a bit of a thicker full width half maximum. So it kind of fluctuates in between the full width half maximum and the different parameters you can play with there. So, but it is within that ballpark of what the others were achieving.
Yeah. Yes, and with respect to the energy change in a flattening filter free beam, I guess if you're changing the energy, it's going to change the depth dose down the central axis.
Yes.
But it'll also change the shape of the profiles. Do you know what the relative impact was on each? So the error that you were accumulating, the sum of squares differences, was that mainly coming from between profiles, or was it within profiles? So was the shape of the profile changing considerably as well?
So going through, where did this see this one here? So the shape of the profile in itself, as you can see, so this was just for one energy. It did decrease quite relative to what we expected with the commissioning data. Most of them were really accurate in itself. Well, not really accurate, so they were quite similar. So I think if I go to this penumbra one here, this nice cyan and blue one, I think, should be the simulated data on this case here. No, sorry, the commissioning data. And then, as you can see, all these different values, all the different these are all the different energy values that you can have with it. So it is quite similar with it, but we're just trying to look to see what minimised the error. In terms of the comparison between the central axis comparison to the XY profile ones, that's something I didn't quite get around to doing that comparison with. However, that is something that can get looked at, because we do have that data to make that comparison. I just unfortunately didn't get around to doing that.
Yeah, no, that's fine. Thanks.
Good, yeah.
Hey James, great presentation.
Cheers, mate.
If you just go back to that visualization you had of the Linac head, was that your phase-based plane shown by the grey circular plane?
That is correct.
Yeah. So were you looking at a number of different field sizes in this, or was it just the 140 by 40 centimeter field?
So I did go through the intent was to look at a number of different field sizes, and I got to the 10 centimeter by 10 centimeter comparison one there. But that was the only other one I was able to achieve with that in itself. So, and to start off with, the calibration was done solely with the 40 centimeter by 40 centimeter field, particularly because that's the hardest one to get right, because we're taking the error across a much broader size in itself there.
All right, yeah, I guess that makes sense. I was a little confused why that phase-based plane is before the jaws rather than after, but I guess if you're looking at a couple of different field sizes, that makes more sense.
Yeah, so the intent was to calibrate them all just before that, just before those jaws, so that in future work, if you did need to change those field sizes, it's a much you can still save the computational time to go ahead with that.
Yeah, perfect. All right, cheers.
Great. Any other questions from James? Very good. If there is no more questions, thanks very much, James. Just nice work.
Beautiful. Thank you all very much for attending.
Excellent. So now I'll stop recording.